Hello again. This is going to be the second of my 3 talks on singularities of the Lagrangian mean curvature flow. So today I will be talking about neck pinches. And again, all of this is joint work with Jason Lotte and Felix Schulze. Okay, so the setup is basically exactly what we were discussing before. So now LT is what I'm going to call a solution of the Lagrangian mean curvature flow inside C2. And we have some existence time under some capital T, and we would like to analyze a singularity at this capital T. So to say things that are precise, let me add what are the technical assumptions that we need to have. So the initial Lagrangian L0 needs to have uniformly bounded area ratios. It needs to have a uniformly bounded Lagrangian angle. And both of these conditions can be shown to be preserved along the flow. And then finally, we need a kind of topological condition. So let me just assume that L0 is exact. So this means that this Liouville form, when restricted to L, is exact. So notice that it's always closed because d lambda is the same as 2 omega, and by assumption, omega restricted to L is 0. Okay, so this lambda, which is always closed, is required to be exact. More generally, one could ask for it to be what's called rational. All right, so we are always assuming these basic things, and the main result that I will be discussing today is the following theorem, joined with Lotte and Schulze. So this says that suppose we assume that this x at this final time, capital T, there's only one singular point, namely x sub capital T. And let's suppose that at this singularity, there is a tangent flow, which is given by a union P1, union P2, which is a union of 2 transverse planes with multiplicity 1. So we don't allow any double planes. Okay, so suppose a tangent flow is a transverse union of multiplicity 1 planes. Then this tangent flow is unique. So remember, the tangent flow is defined by taking some subsequential limit of a sequence of blowups. And the uniqueness just says that this limit that you obtain is independent of what sequence of blowups you take. I should point out that one can already rule out lots of things by the following result due to Neves. So he showed that if there is a singularity, then the tangent flow that you see has to be special Lagrangian. In other words, the Lagrangian angle of these 2 planes has to be the same. For if it were not, then he showed that in fact there is no singularity forming. So of course, you could have such a tangent flow. For example, if your flow is immersed, you could just have 2 smooth components meeting at a point, and then the tangent flow at that point would simply be the union of the 2 tangent planes. Okay, so that could be any 2 Lagrangian planes, but the curvature is not blowing up. This would still be a smooth flow. So if there's a genuine singularity forming, then Neves showed that both angles have to be the same. And this result has some interesting geometric corollaries. The first one is that in the setting where you have a singularity that has a tangent flow given by 2 transverse planes, one can show that we can actually continue the flow past this point. So in fact, what will happen is that at the singular time, one can show that using the uniqueness of the tangent flow, at the singular time, we have a C1 surface, a C1 immersed surface, and then one can show that the flow can be continued with this C1 initial condition. And I mean, it will continue as an immersed flow. The second corollary is that If you have such a tangent flow, then a suitable blow-up limit, so if we choose the blow-up, the centers of our blow-ups correctly and the scales, then what we will get is what's called a Lawler neck. So this is simply this complex hyperbola if you choose suitable complex coordinates. So these would not be with the standard coordinates on C2, but a kind of rotated complex coordinates for some rotated complex structure. Okay, or in a more basic sense, if you see this two planes tangent flow, then geometrically what's happening is that you have locally the flow looks like this family of surfaces. So these hyperbolas where the neck collapses to a point in the limit. So it gives us this nice geometric understanding of the singularity formation. Okay, so in this talk, I'll basically I'd like to give a kind of overview of how to prove this theorem. So how to prove the uniqueness of the tangent flow. Okay, so first, let me give some sort of basic remarks on tangent flows. So it turns out that instead of considering different parabolic rescalings and then taking a limit, it's much more convenient to sort of do all the parabolic rescalings at the same time and consider this rescaled flow. So essentially for each time S, this would be a time slice of one of those parabolic rescalings that we were considering before. So now this is not a parabolic rescaling, so it no longer satisfies the mean curvature flow, but rather it satisfies the so-called rescaled mean curvature flow. So there's this extra normal component. Okay, so it's like mean curvature flow, but at the same time you're sort of trying to expand out by some rate. Okay, so as I said, the different time slices MS can be viewed as the -1 time slices of a certain rescaling L tilde. So here you can see the formula precisely. So if you fix S and you now consider this rescaling L tilde sub t given by this formula, then the t equals -1 slice of this. So this is a parabolic rescaling for any fixed number S, and the -1 time slice of this is exactly this S time slice of the rescaled flow. Okay, so you're combining all of these -1 time slices of all the parabolic rescalings into a single flow. So the effect of this is that the tangent flow is extracted as limits of this rescaled flow as S goes to infinity. Okay. And there's this crucial monotonicity formula due to Huysken, which, so along the usual mean curvature flow, there you have a kind of heat kernel factor that's changing scales. Along the rescaled flow, it has a sort of simpler version. It's this. So if you look at on the time slice MS, you look at this Gaussian area, then the monotonicity formula says that this is decreasing. And in fact, the derivative is given exactly by this quantity. In particular, the static solutions. So if you have this quantity equal to 0, which is, it's called a shrinker for the mean curvature flow, then the rescaled flow is not doing anything. And then indeed the monotonicity formula says that that's exactly the situation when this Gaussian area is not changing. Okay, so basically the rescaled flow is a gradient flow for this Gaussian area. Okay, so this is true for any mean curvature flow. In the Lagrangian case, there's this extra structure given by the Lagrangian angle, and a crucial fact is that the Lagrangian angle satisfies a nice evolution equation. So along the the regular mean curvature flow, it satisfies the heat equation, and along the rescaled mean curvature flow, it satisfies this so-called drift heat equation. So it has this extra drift term that's coming from this extra scaling along the rescaled flow. And then a generalization of the monotonicity formula applies to basically any quantity that satisfies the drift heat equation. And it says the following. So it's actually an equality. I'm just throwing away a term that I don't need here. So for the angle, it tells us this, that if I look at this Gaussian L2 norm of theta, then this is monotonically decreasing. And in fact, the derivative is given by the Gaussian L2 norm of the mean curvature. So this comes from the fact that mean curvature is J nabla theta. Sorry, J nabla theta. Okay, so now if you look at these two monotonicity formulas, so the Gaussian area is decreasing, it's always positive and decreasing. L2 norm of theta is positive and decreasing. Well, this says that along any limit, so along any subsequence, so any sequence of times s going to infinity, and the limit, these things, these derivatives will have to vanish. Okay, so we obtain this kind of result, at least along like subsequences. Okay, so this is just obtained as a combination of these two monotonicity formulas. So here you have h plus x perp over 2. Here you have h, so you can separate out h and x perp. So this is at the heart of Nevis's result, that the tangent flows are always unions of special Lagrangian cones, because these two quantities going to 0 mean that on the one hand you're minimal because h goes to 0. On the other hand, you're a cone because this perpendicular component of x goes to 0. Okay. Okay, so now let me discuss a strategy of how one shows uniqueness of a tangent flow. Okay, so the basic issue is, let me go back again for a second to this point. So along our rescaled flow, what we know, what our assumption is, that along some sequence of times, these time slices ms converge to the two transverse planes. The issue is that along a different sequence of times, you could converge to a different union of planes. So, and C2, any tangent flow will be a union of planes. And from the monotonicity of the Gaussian area, we know that any possible limit in our situation will be two planes. It cannot be more or fewer planes. It will always be a union of two planes. By the monotonicity of this quantity, that theta is decreasing, one can see that if our two planes have the same Lagrangian angle, then any other two planes that you get in the limit will also all have the same Lagrangian angle. The issue is that you could still have a different limit, which is, for example, a double plane or a different transverse union of two planes with the same Lagrangian angle. And that's what we want to rule out. Okay, so here is a general strategy of what one would like to do to prove uniqueness of the tangent flow. Essentially, what you want to show is that at some point, once our rescaled flow is already very, very close to our candidate tangent flow, which now I'm going to denote by V0, so this union of two planes, then I can somehow say that we don't go very far from this V0 anymore. So everything boils down to somehow understanding rescaled mean curvature flows that are very, very close to a union of two planes. Okay, you want to then show that somehow then you can no longer sort of drift away from these two planes to a different union of two planes. Well, since you're very close to two planes, what you'd like to do is somehow linearize the problem. So on a large region where, like, away from the origin and away from infinity, you will be able to write such a flow as a very small graph over the two planes, and you can approximate the mean curvature flow by its linearization. So for the rescaled mean curvature flow, the linearization looks like this. So it's a kind of drift heat equation with this extra term coming from this term is coming from this x perp in the formula for the rescaled mean curvature flow. And then what you should imagine is that we're trying to say that our flow ms has behavior that's very similar to a solution of this linear equation. And this linear equation is an equation on our tangent flow, which is a union of two planes. Okay, so one would like to then understand what are solutions to this drift heat equation on the union of two planes. Well, we can decompose the solution V into pieces according to eigenfunctions of this drift, of the drift Laplacian. It turns out that, I mean, this is a very general fact for these linear heat type equations, that we can decompose V into three pieces. There's a static term, which does not change in time. There's a term that collects all the pieces that grow exponentially in time. And then there's a term of collecting the pieces that decay exponentially in time. So I'll call these V0, V plus, and V minus. Okay. What the very best situation would be if all we would see is this. I'm sorry. If all we would see is this piece of the decaying terms. So if all you would ever see is this part, what that would mean is, if, at least on a very heuristic, naive level, what that would be saying is that your mean curvature flow that's very close to two planes actually has to kind of decay towards it at a later time. So certainly then you would not expect that you like drift away to some other union of two planes. So these pieces, if you see these, then that's somehow quite bad, because this would mean that you're sort of exponentially quickly veering away from your union of two planes. But in fact, it turns out that, again, this is a very general phenomenon, that this can be ruled out. You can essentially show that the flow cannot behave to leading order like one of these exponentially growing solutions of the linearized problem. The basic idea is that if you would be growing away at an exponential rate, then at some point you would not look like any union of two planes. But the point is that we know that every possible tangent flow is a union of two planes. So, at a later time, we may look like a different union of two planes, but this growing behavior can be used to show that actually that would not happen. You would not look like any planes at all, because you're somehow like going off exponentially quickly. So in fact, this part is not so hard to eliminate. The most difficult problem is to get rid of the static pieces. In principle, it should not worry us, because it's not changing in time. So it's just it's saying that you're kind of equally close to the two planes at a later time. But the issue is that it's this is only the linearized problem. So it may well be that even if on the linearized level you don't change at all, it could be that the nonlinear equation is still has some lower order behavior that you don't see, and it could still very slowly be drifting to a different union of two planes. So you really want to somehow eliminate the possibility of this kind of term. Okay, so here is the heuristic argument that one would like to use. So this static component V0, so this, you should have in most problems, you would like it to have a geometric meaning. In this case, it simply corresponds to rotating the two planes. So there are a lot of technical difficulties here coming from the fact that two planes, the union has a singularity at the origin, but morally you should think of a solution like this to be just kind of two independent solutions on the two planes. And on any given plane, one can study this drift heat equation, and it turns out that the static pieces are exactly corresponding to simply rotating the plane to a different plane. In our case, a different Lagrangian plane. Okay, so that means that I should not have been writing my flow as a graph over V0. Instead, I should have been writing it over the graph of a different union of two planes. Because if I do that, then I can just get rid of this component. Okay, this is just the static component, and I can try to eliminate it by changing my reference cone to a different one. Okay, so this is, in some sense, this step is what is normally called integrability in these kinds of problems. So in this setting, in a certain sense, you can view it as an integrable situation. Okay, then as I said, one can show with a fairly standard argument that the growing component can be assumed to be negligible. So then what this means is that relative to this new pair of cones V1, we would expect that we decay towards it. So if at some time we were at a kind of distance d from our original V0, then there should be some perturbed cone V1, which is within distance d from our V0, such that the fluid decays towards V1. Okay, so maybe at a much later time, say if you add some big number b, then now I can arrange that I'm at most distance d over 2 from this new pair of planes V1. Okay, and if this really worked, then you would like to iterate this. So look at this. So if you iterate it, then at each step, I'm getting closer and closer to my cone, say Vj. So at each stage, we'll be able to arrange this, that I'm at this, like I always divide the distance by 2. And to get to the next stage, I might have to perturb my cone Vj a little bit to a Vj plus 1, but the size of that perturbation is controlled by the same quantity. Okay, and then this, we can just add up all the distances. So you look at the distance from Vj to V0, so you just sum these quantities, and then in the end you obtain that the distance from this S plus Jb. So notice that J is arbitrary here. So the distance from this time slice to our original cone V0 will be bounded by some constant times uniform constant times d. And this is true for all J. So again, I mean, there's still some sort of fairly standard technical work here, but it's not hard to show that if you know something like this, and you know this for any d, I mean, I could have started at a much later time at which I'm much closer to this cone V0, then this type of statements implies the uniqueness. Okay, so this is basically what you want to show that V0 is the unique limit. Okay, so this sounds very good, and it works in simpler situations, but there are two very major difficulties in our setting. So the first major difficulty is these 2 points that I've listed here. So it's basically that V0 is not a smooth, compact manifold or flow. On the one hand, you have a singularity at the origin. On the other hand, it's non-compact. So it turns out that the real issue is this singularity at the origin, and the non-compactness is something that one can deal with. So indeed, there are earlier results on uniqueness of non-compact tangent flows due to Kolding, Minicozzi, and also Chodosh and Schulze. But our result is the first one that is able to deal with with singular tangent flows. Okay, so just to recap, the issue here is that near zero, we cannot approximate the nonlinear equation with the linear equation because it's the flow does not need to be like graphical in any way. We only know this very weak compactness result, which says that our flow will be close, say, in the Hausdorff sense to V0. And wherever V0 is singular, then this doesn't really help in linearizing the problem. Okay, so what you want to do to overcome this is to prove a non-concentration result. So this would mean that even though near zero, the linearized problem may not model the solution very well, you want to show that all these effects near zero that you have are negligible, and the same thing at infinity. So you want to show that the behavior of the flow does not concentrate near zero and infinity. Okay, so as I said, the infinity is a slightly easier question. So let me focus on what happens near zero. So here, it's very crucial that we work in C2, because in that case, if you have a special Lagrangian union of two planes, then as I said before, we can change our complex structure on C2 by a hyperkähler rotation. And in fact, V0 will be the zero set of this quadratic Z times W. Then there is this crucial observation that on any Lagrangian plane, we will have an inequality of this form. So these two functions, Z and W, which were complex functions for this hyperkähler rotated complex structure, they have this property. So here, as is written here, so theta 0 is the Lagrangian angle of the special Lagrangian cone V0, and theta p is the Lagrangian angle of the Lagrangian plane P that we're looking at. Okay, so I can just say that morally, the reason why this is correct is that if the angle of P were equal to theta 0, so if the right-hand side were 0, then Z and W would actually be complex holomorphic functions for this hyperkähler rotated complex structure, and then that will imply that this quantity is 0. It comes from the fact that Z, W, and Z times W will all be harmonic on P in the case where the right-hand side is 0. Okay, so from this inequality, one can show the following. So we look at the evolution of this quantity, Z times W in absolute value, plus this difference in the angles, so the relative angle compared to our special Lagrangian cone. And it turns out that this satisfies this nice differential inequality. So now we apply the monotonicity formula and observe that what is this ZW? So it's I'm sorry, there is no square here. Okay, so this ZW product, this is actually comparable to X times the distance from V0. So here X is just the coordinate function, so the position vector in C2. So this is just distance from the origin. This is distance from the plane V0. Okay. So modulo this extra factor of X, the point is that this quantity is essentially measuring the distance from our plane V0. So now, because we have this very nice differential inequality, the monotonicity formula implies that an integral bound for this quantity will imply pointwise bounds at a later time. And this is exactly a kind of non-concentration result, because it says that this quantity cannot mainly be concentrated in a small region. So like if it's very concentrated in a small region at some time, then the kind of integral norm of this will be relatively small, and then at a later time the pointwise norm will be small. So the small concentration in a small region will dissipate very quickly. Okay, so this non-concentration result is essentially enough to overcome the main problems with having a singularity at the origin, but it gives rise to a new technical difficulty, which turns out to be really the most technical part of the paper. So the problem is that this non-concentration idea only works when we use a special Lagrangian cone. So, for example, this V0 or other special Lagrangian cones as our reference cone. So if we go back to what we were doing, so our heuristic idea was this idea that we keep changing our reference cone as we move to eliminate this static piece of the linearization at each stage. But the non-concentration only works if this Vj keeps being special Lagrangian. But as I said, the linearization of the equation is just the only thing we can see is two independent solutions on the two planes. So there is no reason whatsoever for the V0 on the two planes to be such that they both have the same angle after this perturbation. On each plane, you get a rotation to a different Lagrangian plane, but these two are completely independent of each other. So if we were at a certain stage in this procedure where you could even imagine that none of these terms exist, you could just ignore them, and the only thing that is remaining is this V0, then still it could happen that V0 simply corresponds to completely changing the angles of the two planes in an opposite direction. And then the effect would be that our flow is now very close to this non-special Lagrangian cone. Then you'd like to keep doing the same argument, but it only works if you have this non-concentration result. But we don't, because this new reference cone is not special Lagrangian. So in this sense, one could think that actually the situation is a little bit more like the non-integrable setting of these sort of tangent cone or tangent flow problems. Okay, well, so as I said, in this case, our heuristic argument breaks down because of having to use this new reference cone, which is not special Lagrangian. But if one thinks about this a little bit, geometrically, this would mean that you have some flow which is extremely close to a union of Lagrangian planes that have a different angle. So a kind of limiting version of this would be to have a tangent flow, which is given by a non-special Lagrangian union of planes. But as I mentioned before, Neves has a result that says that actually this cannot happen. So if your tangent flow was given by a non-special Lagrangian transverse union, then actually no singularity is forming. Okay, so in this case, what you want to do is prove a kind of quantitative version of Neves's result, which says that actually we cannot even be very, very close to a non-special Lagrangian union, but it's a very technical part of the argument because you really need to quantitatively control all of these different sizes. So it's not possible to just pass to some limit and argue using Neves's theorem. Okay, so I think this is my outline of the proof. So the main ideas are you'd like to linearize the equation, then you need to overcome the presence of the singularity in the tangent flow. You can do this with a non-concentration type idea, which is based on this evolution of this quantity ZW. But there's this caveat that you have to somehow rule out the situation where the flow is very close to two planes that have different Lagrangian angles. Okay, so thank you very much for listening.